A steel plate of dimensions 20 mm by 2 mm, that is 20 mm is the width and 2 mm is the thickness, is bent into circular arc of radius equal to 2 meter by applying the end couples. If the Young modulus is equal to 200 gigapascal, find the end couples applied and the maximum stress in the bar. So we'll consider here one steel plate of length equal to L. This one is representing the cross section, and we have width is equal to 20 mm and total thickness equal to 2 mm. So we have 1 mm and we have 1 mm. Total is together equal to 2 mm. This is bent into a circular arc of radius equal to 2 meter. So this one is representing our neutral axis. NA is represented by dotted line and we bend it by an arc radius equal to 2 meter. So this plate is bent in a circular arc of radius equal to 2 meter. So this one is same as radius equal to 2 meter. Here this distance will be same as the distance equal to 1 mm. So rho represents here the radius of curvature. Radius of curvature is same as 2 plus 1 mm, that will be equal to 2.001 meter. Now this plate is bent because of we are applied a couple here, and this one is a case of hogging condition. So this will be taken as a negative value. The maximum stress is developed on the top fiber or bottom fiber, and for this one the top fiber distance is y top is same as equal to 1 mm. Since we have given here the value of Young modulus and we are knowing the radius of curvature, so we can solve this problem by applying the flexure formula. According to the flexure formula, the bending moment M divided by I is same as E divided by the radius of curvature rho. So first term we can find out here what is the end couple, that is the bending moment we can find out. So we have value of M is same as E multiplied by I divided by rho. Value of Young modulus is given as 200 gigapascal is 200 into 10 to the power 3. This time we have width is equal to 20 and the height h is equal to 2 mm. It means that the moment of inertia is bh cube. So we have b is equal to 20, h cube is equal to 2 cube divided by 12, and is further divided by rho. Rho is equal to 2.001 meter is same as equal to 2001 mm. Solve this, you will get this answer in Newton mm. So you will get here bending moment M, that is a couple is equal to 1333.33, that will be Newton mm. Divide by 1000 here, you will get this answer is 1.33. So very small bending moment is required because the section is very thin. In addition to this, we want to calculate the maximum bending stress. Maximum bending stress will be either on the top or either on bottom. Now we want to calculate here what is the maximum bending stress. Maximum bending stress will be tension on the top fiber and compression on the bottom fiber. And we have a flexure formula is M by I is equal to E by radius of curvature is same as equal to sigma maximum divided by C. Here value of C for top and bottom fiber is same as equal to 1 mm. So we have a maximum bending stress will be equal to E multiplied by C divided by rho. Young modulus here is equal to 200 into 10 to the power 3. C value will be same as equal to the value of either top fiber or bottom fiber in the case of rectangular section is equal to 1. And the radius of curvature is 2.001 meter is same as equal to 2001 mm. So approximately here the maximum bending stress is very close to 100 megapascal. And this value of a maximum bending stress is tension for the top fiber and the compression for bottom fiber. A steel band saw blade with a rectangular cross section passes over a pulley of radius equal to 600 mm. So we have given here pulley and the radius of the pulley is equal to 600 mm. So the radius of the pulley here is given as 600 mm. Neglect the teeth of the saw blade and assume that the neutral surface passes through the center of the saw blade cross section. Determine the maximum strain in the saw blade if the thickness of the blade is given as 1.25 mm. So this one is a very thin blade, and the d by 2 is a negligible value here, but we can show here the neutral axis. So approximately we have neutral axis is somewhere here, and this value of the neutral axis will be at a radius equal to rho. So this represents here the radius of curvature. In this case, we have radius of curvature rho is same as equal to r plus we have the thickness divided by 2. Radius of pulley is equal to 600 mm plus we have 1.25 divided by 2. So this one is assumed to be approximately equal to same as equal to 600 mm. So we can use here the flexure formula, which will be same as equal to m by I is same as equal to sigma max divided by c. For rectangular section, c is same as d by 2 is same as equal to e divided by radius of curvature equal to rho. From this we can calculate the value of sigma max. Sigma max will be same as equal to e, that is the Young modulus divided by rho multiplied by c. And the strain here is epsilon maximum. Epsilon maximum is same as equal to stress, that is sigma max divided by Young modulus. So previously we got the expression of sigma max divided by E is same as C by rho. So in this case the maximum strain will be same as C divided by rho, and the value of C is same as D by 2. So we have D by 2 divided by rho. In this case the depth is 1.25, so we have 1.25 divided by 2 times the radius of curvature rho. Radius of curvature is approximately equal to 600. So 1.25 divided by 1200. So the maximum strain will be very close to 1.041 into 10 to the power minus 3 will be mm per mm. That is a dimensionless. A steel strap having Young modulus equal to 210 gigapascal with a rectangular cross section of width equal to 6 mm, height equal to mm is bent around a solid cylinder of radius equal to r. The maximum permissible tensile stress in the steel strap is given as 200 megapascal. What is the minimum radius r of the cylinder that can be used? So you have to find out here the value of the radius r, and this dotted line here represents the neutral axis, that is the same dotted line here will represent here the neutral axis, and we have neutral axis is from the top and bottom at a distance equal to h by 2. So that is a very small value, actually is 1 mm is very small value. So we can calculate here the radius of curvature rho, and we have radius of curvature rho is same as equal to r plus we have thickness is h, so we have h divided by 2. In addition to this, he has given the value of the maximum bending stress. So maximum value of the bending stress is sigma b max is same as equal to 200 megapascal. And in the case of rectangular section, the value of C will be same as equal to h by 2. That is the top fiber and bottom fiber is at the same distance equal to h by 2. In addition to this, we have given the value of Young modulus. So we can use the flexure formula as m divided by I is same as equal to sigma b maximum divided by c. C is the larger distance of the top and bottom is same in the case of rectangular section is equal to Young modulus E divided by radius of curvature rho. So we are interested to know here the value of radius of curvature rho, that will be same as equal to Young modulus multiplied by C divided by the maximum value of the bending stress, that is sigma b maximum. And the value of the rho is same as r plus h by 2. So we have r plus h by 2. So let's substitute here. We have Young modulus equal to 210 gigapascal. So we have 210 into 10 to the power 3. Value of C here is same as h by 2. H is equal to 1 mm. So we have 1 divided by 2. Bending stress you have to use in megapascal is 200. So we have 200. On the right hand side we have value of R is to be find out, plus we have h by 2. H by 2 is same as equal to 1 mm divided by 2. Solve this, you will get the value of R. So in this case, the radius of the cylinder is close to 525 mm. A steel strap of length L meter is bent to form a circle as shown in the figure, and its ends are butt welded together as shown in figure. So this total length will be same as equal to the circumference, and we have circumference is same as equal to 2 pi multiplied by radius r. We assume here the thickness is very small because it is given as 1 mm. So let's say here a rho represents the radius of curvature. In that case, we have length L will be same as equal to the circumference. So we have length L is same as equal to 2 pi multiplied by the radius of curvature. This height is given as h here. So in that case, the maximum value is C will be equal to h by 2. We assume here the section is rectangular. In addition to this, he has given us the maximum value of the strain, that is epsilon max equal to 2 into 10 to the power minus 3. That will be mm per mm. So let's use here first the flexure formula. We have m by I is same as equal to sigma b maximum divided by the maximum distance from the neutral fiber is equal to C of top or bottom fiber is same as equal to egg modulus divided by radius of curvature rho. We'll use the last two term here, and we have sigma b maximum divided by E is same as equal to the maximum strain. So we have maximum strain epsilon max will be equal to sigma b maximum, that is the maximum value of the bending stress, divided by we have egg modulus E is same as equal to C by rho. C divided by rho. Now the value of rho we can calculate here. Once we can calculate the value of rho, we can calculate the value of L also. So maximum strain here is equal to 2 into 10 to the power minus 3. Value of C will be h by 2, that equal to 1 mm divided by 2. So we have 1 divided by 2 divided by rho. So rho will be shifted on the left hand side. We have 1 divided by 2 and again 2. So we have 1 divided by 4 into 10 to the power minus 3. That is, we have 1000 divided by 4. We'll get here the radius of curvature is close to 250 mm. Once we know the radius of curvature, we can calculate here the length L. Length L is same as equal to 2 pi multiplied by rho, which is equal to 250. So approximate length required will be equal to 1571 mm. That is equal to 1.571 will be meter. Almost similar problem here, except that we have circular cross section here. A copper wire having a diameter equal to d is equal to 3 mm is bent into circle and held with the just end touching as shown in figure. The maximum permissible strain in the copper is 0.0024. The shortest length L of the wire that can be used, you have to find out. So this total length L will be same as equal to the circumference. So somewhere we have a neutral axis here and we have radius of curvature equal to rho. So L represent here the circumference, and we have circumference is same as equal to 2 pi into the mean radius. Mean radius is same as equal to the radius of curvature rho. Diameter here is given as equal to 3 mm, and for circular section we know that the maximum value of the top and bottom fiber is a distance equal to d by 2. So value of C here is same as equal to d by 2, that equal to 1.5 mm. In addition to this, we have given the maximum value of the strain, that is epsilon max is given is equal to 0.0024. And we have to calculate here the value of L. So for this purpose, we'll calculate the value of rho first. So again, this time we'll use the flexure formula, that is m by I is same as equal to the maximum value of a bending stress, that is sigma b max divided by C is equal to egg modulus divided by radius of curvature. Sigma b maximum divided by E is same as equal to the maximum strain. So in this case, we have maximum strain is equal to the maximum value of a bending stress that equal to sigma b max divided by the egg modulus E. And this value is same as equal to C divided by rho. This time we can substitute for maximum strain equal to 0.0024. Value of C is same as d by 2 equal to 1.5 divided by rho. So 1.5 divided by 0.0024, we can calculate here the radius of curvature rho. So in this case, radius of curvature rho come out to be 625 mm. Once we know the value of radius of curvature, we can calculate the length L, which is given as 2 pi multiplied by rho, and we have rho is equal to 625. So in this fashion we can calculate total length. This total length will come out to be 3925, that will be mm, is same as equal to 3.925 will be meter. When a steel wire is bent around a cylindrical drum of radius r equal to 32 centimeter, the maximum normal strain in micron you have to calculate, and we are given the diameter d equal to 1 by 16 cm. So diameter is known, radius is known. So approximately we can show here in somewhere between d by 2 we have neutral axis, and this neutral axis from the center has a radius of curvature equal to rho. So the value of rho is same as equal to the radius of the drum r plus v of d by 2. In this case the value of radius is given as 32 cm. So we have 32 cm plus diameter d is equal to 1 by 16, that is 1 divided by 16 and 2 is 32. This answer will come in cm, is approximately again equal to 32 cm. 1 by 32 is very small value, is close to 320 mm. Maximum strain we have to calculate here. And for circular section here, the value of C, that is the distance of the top fiber or bottom from the neutral axis, is same as equal to d by 2. That is we have 1 divided by 320 will be mm. We have a same flexure formula this time. We have sigma b maximum divided by the C equal to egg modulus divided by radius of curvature equal to rho. Sigma b by max divided by E is same as the maximum strain. So we have maximum strain is given as the maximum stress divided by egg modulus. Sigma b by E is same as C by rho. So we have C divided by rho. Value of C is same as equal to 1 by 320, and the radius of curvature rho is also approximately equal to 320. So approximately you will get the strain here is 975.6 into 10 to the power minus 6 will be mm per mm. 1 micron is 10 to the power minus 6. So your maximum strain come out to be 975.6 micron. The video you are watching is from the app, which is the Mode Class app available on Google Store. And in this app, we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.